Right, so far we have not, I told you guys I was going to show you how to do the reverse chain rule, and we have not done anything with that. We haven't had a problem yet where we couldn't distribute in that coefficient out front inside of the function and then expand it so that we could do each term individually. If you notice, because this has the square root with two terms being added together, there is no way to separate it. So we use what's called U substitution. Basically, it's just a way to rewrite. If you notice, this seems like a complicated mess. Kind of looks like the chain rule with the g prime outside, which would be the inside function's derivative. But we just kind of look at this, that it's a mess, and we want to make it look nice and neat. So that's what we're going to do. I'm going to show you, I guess I'm going to walk you through kind of how I think about these problems. You don't have to do it my way, but it definitely works really well for me anyway. So the way that I pick who U should be is I always ask myself, one of these has to be some form of the derivative of the other. So in other words, I always say there's two ideas. These are my two ideas in this function. Now one of them has some form of a derivative of the other. Since this guy right here is 1 plus x squared, and this is 2x, I know 2x is a form of the derivative of x squared. So the one you could think of that is basically the antiderivative, or the one that could be considered the original function, is always your u, and then the other one is going to be the derivative of it. So I'm looking at this and I say, okay, I want this whole thing to be my u. So I'm going to say u equals 1 plus x squared. Now, if u equals 1 plus x squared, then if I do the derivative of u with respect to x, I'm going to get 2x. If you notice, that is this 2x right here. All right, but I also have a dx, and I need a dx because I'm going to do substitution, so I want to substitute something in for the 2x and the dx. Well, I notice that if I go ahead and I multiply this by dx, and I multiply this by dx, I get du equals 2x dx. All right, so we are actually ready to do our substitution, because between this guy and this guy, I have everything that's inside of this. All right, so we have the integral. I'm going to do a substitution here. We are square rooting u. That's what we're doing, because u is 1 plus x squared, and we're taking the square root of 1 plus x squared. And then I'm going to go ahead and tack on our du. And actually, that's done, and now we're ready to do the antiderivative. But let's talk about why. If you notice, this guy right here replaces this guy right here. And then the du replaces these two things. So this integral right here has, using all of this substitution, has the exact same meaning as the integral, the original integral. All right, so now I'm going to go ahead and rewrite this as u to the 1/2 du. And if I do its antiderivative, I would have u to the 3/2 over 3/2 plus c. But I know that I can reduce that a little bit more, and I would have 2/3 u to the 3/2 plus c. But now, we don't actually want our final answer to be in terms of u. We want our final answer to still be in terms of x. So now we just do a back substitution, and we'll have 2/3 out front, and then we'd have u, which we said was x, or 1 plus x squared, to the 3/2 plus c. So our final step is to get it back in terms of x. So we turn it into u, so it's nice and simple to do the derivative or antiderivative of, but then in our final answer we still want it to be in terms of x. So again, just kind of to recap on this, I know I got a lot of colors going on this page, but basically we are literally just rewriting the integral so that it's this nice little compact problem to do the antiderivative of, and then we plug back in the original stuff so that it's not in terms of u anymore, it's back into terms of x. All right, let's try another example. All right, so just like on the last problem, when I look at this, I ask myself, who looks like an antiderivative and who looks like a derivative. But you first have to be able to recognize that there are two functions. We have two things going on here. I see an x cubed as one function, and then the cosine of this kind of mess, this x to the fourth plus 2. So I ask myself, which one of those parts has an antiderivative of the other, or which one has a derivative? Well, I know that the derivative of x to the fourth is x cubed. So that makes my decision easy for who u should be. So I'm going to make u equal always to the form of the antiderivative. And now so far these have been pretty perfect, but I'll show you on this one how it's not always perfect. So looking at this, we have our u. If we go ahead and do our du dx, I would get 4x cubed for my derivative. And if you notice, this is not 4x cubed, it's just x cubed. Plus, I need to account for the dx, so I need to somehow get those two together. So there's one really simple way to do this. Solve so that it looks like x cubed dx. Well, in order for that to happen, I need to multiply both sides by dx. So I'm going to go ahead and multiply both sides by dx, and I'm close. I still have that 4 out front. So then I just go ahead and divide both sides by 4. So I get 1/4 of du would equal an x cubed dx. All right, now that we have the x cubed and the dx, which I needed, and I have the u, which I needed, we're ready to write the integral in terms of u. So I have the integral, and then I'm going to write that it would be cosine of u, because I'm replacing that x to the fourth plus 2 with u. And then I'm not just going to add a du, because a du wasn't enough. I have to add a 1/4 du, and that's going to account for the x cubed dx. So again, let's take a look at this. I'm going to go ahead and erase this and just kind of walk you back through how it all works. All right, so I have cosine of u. So cosine of u, and that fits. So this is taken care of with this part. Then I have the x cubed and the dx taken care of because 1/4 of du equals x cubed dx. So that's taken care of with the other two parts. So I've completely rewritten the integral in terms of u. And now I'm ready to do the antiderivative. So we have 1/4 is out front. The antiderivative of cosine is sine plus c. And again, my final step on this is to always put it back in terms of x. So I'm going to go ahead and replace the u with what it's equal to, which is x to the fourth plus 2 plus c. And you could always verify that its derivative gets you back to what's under the integral. All right, so let's do our next example. You might be looking at this one wondering, well, I don't see a derivative and an antiderivative in this. But if we think about it, we can't separate this guy. I can't make it square root of 1 plus square root of 2x. Like, I don't know how to do that. So I still have to use this method. I just got to think about how it might work. If I make u the 1 plus 2x, because there's really no other option, well then du over dx would equal 2. And if I go ahead and I need a dx, I need du to replace dx always. So I'm going to go ahead and multiply by dx. So I get du equals 2 dx. Now there is no 2 out front here. So I don't want the 2. I'm going to simply divide by it. So 1/2 of a du is going to equal a dx. All right, I think we're ready. We have everything that we need. So we have the integral square root of u. So that just replaced this part because u is 1 plus 2x. So if I take the square root of that, I've got that. Now to replace the dx, in order to replace the dx, I'm going to have to use this guy. So I'm going to replace a dx with a 1/2 du. And now I'm ready to go ahead and take the antiderivative. So I'd have 1/2 out front. This would be u to the 3/2 divided by 3/2 plus c, which would be 1/2 times 2/3 u to the 3/2 plus c. So for our final answer, we would have u to the 3/2, which is 1 plus 2x to the 3/2, over 3 plus c. And maybe you wonder what happened to 2's, but they reduced. All right, got a couple more examples here for you. This really is one of those processes where you just have to practice it. You might want to pause the video and try this one before I go through it or see what you think, but I'm going to go ahead and go through it here, but again, you might want to pause it. Okay, to me it's the obvious choice that u would be 1 minus 4x squared, because that's the big idea, that's the antiderivative of the other, or a form of the antiderivative of the other. So then if I go ahead and just do du dx, I know the derivative of 1 is 1 or 0. Derivative of negative 4x squared then is negative 8x. Now, when I look at this, I see just a 1x dx that needs to be replaced, but I have a negative 8x. So again, just like before, I'm going to multiply both sides by dx, and then I'm going to go ahead and divide by 8 on both sides. Sorry, negative 8. So if you see a negative 1/8 du will equal a dx. And now I'm ready to write my integral. So I have the integral, and in this case, it's going to be 1 over the square root of u. And then I need to tack on a negative 1/8 du in order to account for the x dx. You know what, I just noticed that I forgot to write an x here. So I only divided by negative 8, so sorry, that should have had an x with it. All right, so if I'm going to do the antiderivative of this guy, I would have negative 1 over 8. I'm going to go ahead and rewrite this so that it's u to the negative 1/2. So if I go ahead and do the antiderivative, I have negative 1/8 out front, u to the 1/2 divided by 1/2 plus c. So that's going to equal negative 1/8 times 2 times u to the 1/2 plus c. And so I'm going to get negative 1/4 times the square root of 1 minus 4x squared plus c. You know, a nicer way to write that might be the opposite of 1 minus 4x squared over 4 plus c. All right, again, you might want to go ahead and pause the video and give this a try first, see how you do, or you can just do it with me because I'm going to go ahead. All right, in this case, I'm going to make u equal to 5x. Sometimes it's just very obvious. Anytime you have e to the something, that's going to be your u. All right, so du dx is going to equal 5. So again, I need to solve this. So I have times dx. So du will equal 5 dx. But I notice there's no 5 out in front of the e. So I'm going to make it 1/5 du equals a dx. All right, and I have my integral, e to the u. So that's been replaced. But now I need to replace the dx. Well, in order to replace the dx, I have to go ahead and use 1/5 du. All right, we're ready to take the antiderivative. Antiderivative would be 1/5 e to the u plus c, or e to the 5x over 5 plus c. Okay, so in the last examples, we kept, for our final step, we always rewrote the problem back in terms of x. Well, for actually finding an answer, we don't have to do that if we do it right. So I'm going to show you a little shortcut. You can go ahead and read through the rule here if you want, but I'll just show you how the rule works. So I'm going to go with example 1 here. Okay, it looks very familiar to something that we already did. So my u is going to be 2x plus 1. My du dx would be 2. So if I solve that, I'm going to get d, or 1/2 du equal to dx. All right. Now, if this is a definite integral, so if you have this, you know the domain that you're taking this area over. we simply can rewrite those in terms of u. So if I just plug, I'm going to go ahead and figure out what my new a should be and what my new b should be. If I just plug back in 4 and 0 into the original function, then I'll get what they are in terms of u. So I'm going to plug 0 in to this function right here, this equation. So if I plug it in there, I would get 2 times 0 plus 1, which is 1 for a. And if I plug 4 in, I'll get 2 times 4 plus 1, which is 9. So in other words, I'm just plugging back in the values to u so that I have a new a and b, so they'll be in terms of u as well in the integral. So if I write my integral, I'm going to do my integral now not from 0 to 4, but from 1 to 9, because that's what it would be for a u. And then I'm going to do the square root of u, and I have to put my 1/2 and my du in order to account for the whole thing. So I've replaced these two. I've replaced this, and I've replaced this. So I've rewritten the integral correctly here. All right, so if I go ahead and do the antiderivative, I would get u to the 3/2 over 3/2. I'm going to evaluate that from 1 to 9. So I would get 1/2 2/3, u to the 3/2 from 1 to 9. Just move this up a little bit here. All right, so it looks like I have u to the 3/2 over 3 from 1 to 9. So if I plug 9 into that, and then 1 into that, and subtract them, I will get the area under the curve. Did you notice that I never had to go back in and resubstitute back in the u to get it in terms of x? Because if I rewrite my a and my b so that they go with u, I don't have to do that. I can just get my answer, because either way I'm going to get the same answer. This is just less work in the long run. So 9 to the 3/2 is 27 divided by 3 is going to be 9 minus 1/3. So our final answer will be 8 and 2/3. And now it's perfectly legal for you to go ahead and resubstitute back in the x, but then you don't want to replace the a and b. You want to use the original 0 and 4. But you can go ahead and rewrite those so that you can use the u's and not have to have that extra step in there. Let's do one more example if you need to. All right, I have 2 more examples we can do, but I'm just going to go ahead and do one of them. When we look at this, the obvious choice again for u, so I'm going to keep consistent with the colors, u would be 3 minus 5x. So our du dx will equal -5. So then I would have -1/5 du will equal a dx. And I need to rewrite my a. So if I plug 1 into the u, I would get 3 minus 5 times 1, which is -2. And if I plug 2 in, I get 3 minus 5 times 2, which is -7. Sorry. All right, so I'm ready to rewrite my integral. So I'm going to go integral from -2 to -7. And then I know that this is u to the -2. Then I need to replace the dx, and I know dx equals -1/5 du. So I have replaced everything in it. All right, if I go ahead and take the antiderivative, I would get u to the -1 over -1. I'm going to go from -2 to -7. So I really just get 1 over 5u, because this would become positive, and then this really belongs in the denominator, from -2 to -7. So now if I go ahead and plug that in, I'm going to get, let's see, -1 over 35 minus a -1 over 10. And if you go ahead and do that math, you should get 1/14, it looks like. All right, come on in and see me if you need help. Maybe try example 3 on your own. There are just handwritten notes for that one online. All right, see you guys later.